we've already defined and computed velocities in section 1.5, so we do know that velocity is essentially derivative, okay, the first derivative. In terms of how we're going to set it up, though, in Leibniz, its velocity is ds over dt, so derivative of s respect to time. So because speed comes from time because time's the independent variable, so it's the same thing as dy dx, but ds dt. So just keep that in mind. So basically, this is what you need to know. Velocity is ds dt, which is the derivative with respect to time. And then we're just going to do 2 examples here, and then we'll go to acceleration. So it should be pretty quick. Okay, so the first example here, so we have a stone's dropped from a cliff that's 122.5 meters high. Then its height in meters after t seconds is h, 122.5 minus 4.9 t squared until it hits the ground. Find the velocity after 1 and 2 seconds. When will the stone hit the ground? And with what velocity will it hit the ground? So first off, find the velocity at 1 and 2. That's the same thing as taking the derivative and plugging in 1 and 2. So all we have to do is, if we want to find h prime, because the height in t, okay, that's essentially our relationship for the velocity. So in this case, ds over dt, s in this case is height. Okay, t is still time. So we still are just going to find h prime, and we're going to use h prime for most of these questions. H prime is pretty straightforward. It's negative 9.8 t. So then for the first question, they want to know at 1 and 2 seconds. So we just go h prime of 1, which is negative 9.8. That would be meters a second. And then h prime of 2, negative 19.6 meters a second. So it's falling, right? We know it's falling. So that's A. So B, when will the stone hit the ground? So what does the ground represent? Yeah, 0. Okay, and that's from the original equation. We have nothing to do with velocity. Velocity's not going to help us find when it hits the ground. So we're essentially going to just set this equal to 0. Minus this over. Divide the negative 4.9. I think that I got 25. And then you square root. T is plus or minus 5, but time can only be positive. So at 5 seconds, it's going to hit the ground. And then what's the velocity when it hits the ground? So at what velocity is it hitting the ground? It's the force that it's hitting the ground. We go right back to A, exact same thing, but we're doing of 5 now. So h prime of 5. So that's going to be 49 meters per second when it hits the ground. Okay, nothing too new. Everything's okay with that. Okay, so essentially all I want you to get from that first page is velocity is the first derivative. Okay, second one's a little bit more complicated. The position of a particle moving on a line is given by the equation. So it's a particle that's moving on a line, so we don't know what direction it's going and those things. It's kind of interesting. Where t is measured in seconds to s in meters, but that is the equation of how it's moving. So it is cubic, so we know it's going to change direction 3 times, right? Or 2 times, excuse me, once, twice, okay? So what I mean by that is if we know a parabola, if it was squared, we know it would be something like this, so it changed direction once. Well, with a, oops, that's one too many. With a cubic, it's twice. Okay, it's going to go once, twice, change directions. Okay, so just keeping that in mind, just kind of visually what's going on. So what's the velocity after 3 seconds and 6 seconds? So what do we want to do to find that? Find the derivative. So we're going to find the derivative first. Let's do the derivative anyways. We're going to want that throughout this question. 3t squared. 6, yep. Thank you. 6t squared and minus the 42 plus 60. I'm also going to GCF this, we're going to need that for later. They all have a 6 in common. So then for A, if I plug in 3, see 3 squared is 9, minus 21 is negative 12, negative 2 is going to be negative 12 meters a second. It's meters again. Yep. F prime of 6, when you calculate that, it's going to be 24 meters a second. So that's interesting. So one, it was kind of going down, and one was going up. Okay, so it was positive versus negative. So that means we do have a change. When is the particle at rest? Now focus, what does that mean? When is it at rest? Velocity is 0. Good. So that means we want the derivative to be 0. Exactly right, Keita. So we would essentially set this to 0. That's why I put that there, because now we're going to see, can we factor this? Is there factors of 10 that get you 7? Negative 5 and 2. Good. That means at 5 seconds and at 2 seconds. See, you knew you wanted to use your Math 20 stuff. So 5 seconds and 2 seconds, it's at rest, which means it's switching direction. So this particle is going like this on a line, and so at 2 and 5 seconds is when it changes direction. Okay, I didn't put the picture on here of it, I should have. But when you look in your book, there's a picture of the track that it takes. You can see that picture there if you don't have the book open. See how it's changing direction? That's the equation of it, okay? All right, so that was B. C, when is the particle moving in a positive direction? So how can we figure that out? Well, essentially, we need to understand that these are where it's changing. We got to do our sign analysis on those 3 sections, right? Because we're going to figure out when it's moving positive versus when it's moving negative. We know that, for example, see 6? 6 is bigger than 5. At bigger than 5, it's moving in a positive direction. Right? I don't have to test that. And then 3, in between them, it's a negative. I just need to figure out what's happening on the other side of 2 now if I use my other information. But you can do it just like this. So for C, I like to set mine up like this. 2, 5. I know that after 5 it's positive because of the 6. I know between 2 and 5 it's negative. I need to figure out less than. I would just put 0. 0 is always easy. 0 would be 60. So it's positive here. So it's moving in a positive direction. Less than 2, bigger than 5. We don't want equal to. For C, less than 2, bigger than 5. And then it's obviously, I guess you don't need to put this, but we do know that it has to be bigger than 0, though, because we can't have less than 0 time. Okay. All right, so D, find the total distance traveled by the particle during the first 6 seconds. Let's try to figure out the total distance traveled. the first 6 seconds. How would we do that? Okay, all great points. So to kind of contradict yours, between 0 and 6, it's changing direction, though. So if it went 6, 8, 10, you would get 2, right? So that's okay, though. So then we need to do the intervals of when it's to it's changing. So we want to figure out how far. So essentially what we know based on all this, and if I've lost you, speak up. I kind of like this stuff because it's applied. This is real, okay? We know this particle is going somewhere for 2 seconds, and then 5, and then after 5. And so we need to figure out the distance traveled on those time periods. So essentially our time periods of our distance we want to look at 0 to 2, and we want to look at 2 to 5, 5 to 6. Those are the time periods of travel we want to add up. Does that make sense? Okay, so with that, we're going to do our simple f of 2 minus f of 0, and it's just f, because this is where it's going. Okay, we're not doing velocity, so don't do the derivative. Okay, so simply f of 2 minus f of 0, f of 5 minus f of 2, f of 6 minus f of 5. And then we want to add those up. Okay, we will absolute value this because if it's going in a negative direction, that's still distance, right? So when you get answers in this, it means if you get here, I'll show you. So this one, you're going to get 52 when you calculate this. Okay, is it okay if I don't do that? Just plug the 2 in, plug the 0 in. Okay, this here, you're going to get negative 27, which is we're going to call positive 27 because it just went back 27. So the distance is still 27. And then the 6 to 5, we're going to get 11. So total distance traveled is 90 meters in the 6 seconds. Okay, questions on that? Okay, that's 3.1. We're done. Okay, on to 3.2. Acceleration. So instead of velocity, now we're talking about acceleration. Acceleration is the second derivative. That's why we have higher derivatives. Okay, so we know velocity is the first derivative. Okay, we define acceleration as the derivative of the velocity, which is the second derivative. Okay, so basically what I want to get from this page, acceleration is the second derivative. Okay. Everybody good with that? Okay, so let's go ahead and do the first example. So it says position of a function particle is given by t cubed plus 2t squared plus 2t, where s is measured in meters and t in seconds. Find the velocity and acceleration as a function of time, which means they have t's in them, which they will. So velocity we know is going to be s prime. So s prime is going to be 3t squared plus 4t plus 2 equals velocity. S double prime, 6t plus 4 is acceleration. And so then it asked me to find the acceleration at 3 seconds. So we want to go 22 meters a second. Okay, any questions on that? You good, Mike? What's up? Sure? Okay. Okay. All right, let's do the second example, which is also the last one. All right, so if a ball is thrown directly up with an initial velocity of 24.5 meters a second, then the distance above the ground in meters after t seconds is 24.5 t minus 4.9 t squared. Okay, so I must have cut off the question. So then we're going to go ahead with this one. Oh, okay. So this is, okay, so this is S, so we have to find S prime. Oh, yeah, that's right, okay. Okay, and then our second derivative, so that's our velocity, our acceleration. Is negative 9.8 meters a second. Okay. I want to make sure I don't have anything.